My name is Michael Carrillo.
I'm Maria Loreto.
Good morning, my name is Edward Gomez.
Our senior project name is a micro-hydroelectric power plant. We want to create a micro-hydroelectric power plant that is capable of powering a small house. It must be used close to a stream of water, ideally a river. And in the case it is not close to a river, we will acquire water through rain harvesting. We want it to be easily installed by any customer. We want it to also withstand high temperatures and strong UV rays. Our current competitor is setting a similar system for around $2,200. We want to maintain that budget or a little bit lower.
The motivation behind our project is to bring electricity to remote areas in underdeveloped countries without a stable source of energy. We decided to go with hydroelectric energy because of its untapped potential. Almost 2/3 of the market is not being taken advantage of. This includes places such as South America, Africa, and India. Water is a clean source of energy and is freely available in these areas, which definitely create and reports as a great domestic source of energy that can help them in the long run.
So in order to have a successful design, we first have to do a little bit of background research and in order to understand how these electrical generators work. These generators work following Faraday's law, which states that voltage is proportional to the rate of change in time of the magnetic flux within a circuit. What this means is that we have electromagnets connected to the rotor, and when due to the rotation of the blades, it causes electricity in coils here on the stator. Apart from, now that we understand how the electricity is generated, we see the common type of hydroelectric power plant is the impoundment type, which requires a dam or a reservoir. Apart from that, nowadays there's a big fad in portable hydroelectric generators, such as the E-Stream and the Power Spout, which is widely used in the western United States. Right now the E-Stream goes for $300, which is only used to power small devices such as your iPhone or a lamp. And the Power Spout is being used right now, currently between $2,200 to $2,300, including installation costs for a household. This led to our first alternative design, which involved our generator to generate electricity through the run of river. However, we realized there was certain constraints which involved less efficiency due to the waves in the river, as well as installation difficulties and electrical components. This led to our second alternative design, in which we would have the power plant in underwater, but this also proved to be difficult because we would have to worry about the electrical components, as well as occasional maintenance for the inlet mesh, which we had to worry about certain debris and fishes entering. This now led to our third alternative design, where we would have a Pelton turbine, and we would collect water through rain harvesting. And with the rain harvesting, we would just use gravity in order to move the Pelton turbine and have an output, as you can see on the left side of the box.
So our prototype design, we're choosing, which was alternative 3. It consists of the following: a box, a generator, an inox mesh, and a nozzle. In the box, we're gonna find the turbine, the Pelton turbine. It'll be fitted inside. The generator will be connected to the Pelton turbine through a connecting rod. The inox mesh will serve as a filtration or as a pre-treatment to avoid any clogging in the system. And the nozzle, we will gather water and we will deliver it to the user through a nozzle at the end of the outlet. So in our prototype design components, we can see that the Pelton turbine works exclusively on how well the head of the jet propulsion will input the power. On the second image, the Pelton turbine the Pelton turbine works exclusively on 2 components: the power coming in and the dispersion of the water. The Pelton turbine works very well with hydroelectric power plants because once the liquid propulsion comes in, it doesn't go with the flow of other regular turbines. It falls and it goes through the outlet.
Certain constraints that we have to consider involve the amount of frequency that our power plant will generate, which involves also the amount of RPMs. For example, if we only have 2 magnetic poles, we need to have 3,600 RPMs in order to generate 60 hertz, frequency of 60 hertz. Apart from that, we need we need to consider waterproof sealants to ensure that our electrical components don't get damaged by any external, by weather from the outside, as well as how much water we need to generate for at least 3 hours. Right now, that's our first goal for our prototype, and we just want to make sure we hit that 3-hour mark. Apart from that, we also have a possible diversion design to consider a local river or a waterfall stream so that it may be able to power the generator. And apart from that, certain material such as stainless steel, the grade T304, it does not corrode when it comes in contact with water, so that's definitely a material we want to consider to use.
So once we finalize the CAD model, we are planning on doing some fluid analysis to sort of figure out what kind of reaction forces, moment, and pressures we are dealing with. And then we can import that into structural analysis with the external forces we're expecting. We can run some dynamic vibration force and deflection analysis to make sure that our prototype works. While we were researching the standards, we realized a lot of the hydroelectric standards apply to large hydroelectric facilities, not many to micro hydroelectric facilities. The ones that we were able to find so far have been the IAA standards shown there. However, because microelectricity is relatively new, standards do take a while to go all the way through. So we did notice that there's a standard currently in the proposal for ASTM, which is protective coatings and linings for hydroelectric facilities. This would definitely come into play once it does. For global design, we definitely try to keep our prototype as environmental friendly as we could, since microhydroelectricity does not need the building of a dam or any of the sort. It serves the environment a lot less than regular hydroelectric. And we have to make sure that the water that does go through does not pollute. Since we are considering rain harvesting, most of these people tend to use that water collected to do something else with it. So we want to make sure not to pollute water. So like mentioned in the motivation, we're trying to bring electricity in places where they don't already have a stable source. That electricity has been shown to increase the standard of living, so that definitely helps society as a whole. We do want to have a multilingual manual. So far we have English and Spanish for sure. And if by any chance you don't understand any of these languages, we do want to include pictures and diagrams to show the installation and maintenance procedures. And then for safety considerations, we are considering doing the emergency shuttle plug. If anything were to get inside the turbine, I don't know, something starts going wrong, they have the ability to turn it off before it damages the rest of the generator or anything around it. For our Gantt chart, we get results quite some time for the CAD analysis, mainly because two of us are not going to be here during the summer. We do plan on starting manufacturing as soon as we get back. And for the division of labor, we did choose some task leads based on what they have most experience in. They can sort of like lead us through those tasks.
In conclusion, we finalized our conceptual design stage, and we are finalizing. We should be finished with the final CAD model with our first draft of the CAD model by the end of this month. Once we head into our FEA analysis, we will have an initial material and component selection prior to our FEA analysis, And then once we gather the data from this analysis, we'll be able to conclude our materials and component selection prior to manufacturing and optimization of the design. Thank you. Now we open the floor for any questions.
I have a question on how you're going to hang this or install this. There was a reason why they built dams. So are you going to hang it on a downspout off my roof? Or are you going to get a cistern and drain the water out of the cistern? Or?
Alright, so in the case we do the river, the gathering through the river, right, of the water, it's going to be...
What we were thinking about using is a gutter system. And then now the tank that we were, if we were to do this in a household, we were thinking about using 10 feet tall tanks. Now, of course, this would depend on the house as well, because right now that would give us our most potential energy to use for the water, for electrical generation. We would mount these very easily with simple, I guess, with simple tools that you can use. However, this would, I guess we would have to be, I believe, we might have to use some power tools in order to be able for this to be stable inside by the house. So that would require some insulation help.
So you're going to have to, something accumulates the water.
Yes, so on the rain harvesting, it'll be a tank mounted onto the side of the house. In the case it comes from the river, it's going to be through a cistern, which will have a high altitude, and we will indicate, or we're gonna do a jet-like propulsion into the box with the turbine. Yes.
I have a couple questions. So first thing, again, it goes for where you're going to install this. If you are going to install it, as you mentioned, below or with a tank. To me now, this is not a very green alternative because you're going to have to waste water to power your house. So you're not really eliminating the cost point of it. And what if you don't have water available to just power this turbine? As far as the river goes, if you're near a stream, where this might not be big enough to fit in a stream, so these are just things as you need to focus on one and drive your design to that. Following that, your picture shows a highly complex turbine that I would be very concerned about you getting completed in 6 months. There's variable veins in that picture, tightly controlled tolerances that you would have to take into account. So it's something that I'm a little concerned because I didn't really see a design proposal here today. You mentioned different concepts, but I'm really not sure with what you're going with. You also mentioned the Pelton turbine. For Pelton turbine, it's not a very efficient turbine for streams. Pelton turbines are made for unidirectional flow. So you have a nozzle pointing straight at your collection, like the spoons of the turbine. So if you have a stream where there's multiple directions of flow, it's now not as efficient as if you have airflows on your turbine. Your accessibility and your size, right? If you want to power 4 homes, how big does this thing need to be versus if you're powering, like a camping trip? Something else to consider as far as where you're taking this project to. And then green materials. You touched upon a couple of standards, but anything that has to do with putting it in the water or putting it near drinkable wells or anything like that, you can't use like chrome plating or certain types of coatings that would be detrimental to the environment. So again, a lot of consideration to put into your material choices.
I understand your point, and what I want to say with the green aspect, we are gathering water from the river. we're gonna channel it into closer to the home because I would hope the house is just not beside the river. So for example, it's a couple yards away. We're gonna collect it in a cistern. And from there, with the high altitude, we're gonna channel it into the water. Therefore, we will simulate a jet-like propulsion. In the case of the rain harvesting, it'll come through the gutter system, go to the side of the house, and therefore the same, simulate the jet-like propulsion. You were saying about the pelton. It will work because it has the jet-like propulsion. It's not all over the place. It's going to be in one direction.
Okay, so then I would explain that a little better on whether you're collecting from the river. I initially assumed that you were placing this in the river based on the examples you gave of existing
First
devices.
two designs, correct.
Right,
Yeah.
so I thought that's what you were leaning towards, something you can just stick in a river and it'll power up your house versus, now you need to implement construction, PV the river into something that will power your turbine.
So maybe to follow up a little bit on that too. I think one thing that's really important with any power generation system is the metrics associated with specifically cost per kilowatt hour. That's how they're all judged. Okay. So if you're talking about third world country, that's even more important, right? Because there's minimal money in a third world country for investment of physical things, right? And so every time I think a question comes up, it sounds like there's more and more infrastructure going into the thing that you're making. Again, if you're considering that market, you want to be conscious of that initial investment cost. The other thing is, how much energy are you generating? The only place I really saw this was an average of 1,800 kilowatt hours per year. Okay, so again, be cautious with how you're generating these numbers and how much is necessary. How much would you guess is necessary to power a home? Do you guys have that information?
We actually got 1,800 from an average of countries that we were looking into.
Okay.
And
so this has nothing to do with your design yet. This is just your
this
goal.
is what we're.
So any thought about how much you're going to generate from this?
Based on that number of 1,100, it's around 150 a month. We expect to be around 60 to 100.
But with, I'm not sure you have a final design, so you're confident in that just based off of the information that you have now?
So to further emphasize, that's one of the constraints we have right now in order to finalize our CAD model.
Okay.
And we do not have that number.
Okay. So this is why this part is here, right? So next time when you're here, cost per kilowatt hour, very, very important. I think right now, some of the best are like, I think it's 0.4 cents per kilowatt hour. So you guys have a pretty steep challenge to beat that. I don't know if you have to, right? But if you're 300 cents per kilowatt hour and you need to reconsider your design, okay? And you can use that to guide your design and your goals, right? You can use that to guide it. So if one thing is using rainwater with a spout from the roof, and that gives you $600 per kilowatt hour, don't do that, right? But if there's one, hey, maybe it takes a little more investment, but you can divert some water through a river nearby, but it's 3 cents per kilowatt hour, then use that. I would use that as a guiding force throughout, rather than just kind of design choices, okay?
Make sure you point out the environmental impact of diverting rivers, right? I mean, you can do it, but if it's going to jeopardize the ecosystem that these people live from, point it out.
My questions go to start off with, you had a target cost of about $2,200, and you're telling me that you want to use it in South America, Africa, and India. Is there a way that you could set your goal at something more realistic? Because I think that first thing, the burden of you guys producing a $2,200 device is not right. Your ability to prove these concepts to us with something substantially costing less than that, you can achieve. And so I target you to go after something at least half that, if not more than half that, in actual cost. So that you got something that could be scaled and actually sent to South America, and something that didn't. tear up your bank account.
We chose 2,300 because that is a cost of ours for competition, so we just want to stay below that for sure.
Okay, but
But
set that as a goal. Second thing is, you talked about stainless. This doesn't have to be made out of stainless for your proof of principle. It should be made probably out of something like a plastic model. You do not need to make this. You can tell us that it makes sense to do that in the future, but you don't need to do that for this. Third comment I wanted to make was, you said it needs to produce power in 3 hours sustaining. And when I sit and think about using water from off my roof, where in the country, where in the world are you going to get 3 hours sustaining worth of volume to be able to ensure that I'm going to see 3 hours sustaining? I think you're going to find that that's going to be very hard to do, even in South Florida, where we get 1 hour, you know. And yes, you can collect it, but we'll let game. Have you done the numbers to figure out that that will actually create enough water to give you 3 hours sustaining energy?
Yeah, because as of right now, with the tank that what we envisioned, it would be 10 feet tall. Technically, it would only last approximately like 15 minutes.
And how long would it take to fill a 10-foot tall tank? Okay. And are we ever going to get enough rain, even in the day in South Florida in the middle of the summer, to achieve that goal? So, I mean, with that in mind, maybe the river makes more sense.
Okay.
And focus on the river.
But that's why we had mentioned in our constraint slide a possible diversion design, which would then come into effect we have to be conscious on the environmental friendly aspects and what we can do to minimize those factors.
Your project would be stronger if you make that decision early enough that you can then focus on tighter boundary conditions. Okay.
Alan said it before, you know, keep it simple. Maybe it's better targeted your efforts if you can come up with a design that can be just placed in the river or right next to the shore of the river. It'll also reduce your overall cost. I know you're not getting track of that, but building a 10-foot tank or diverting a river or generating all these structures are going to be added costs that maybe your project won't see, but the people implementing this turbine will see. So just that, don't discard it yet.
Okay.
One of our first designs was that one, and what happens is, in the case of these countries, I personally know I'm from Honduras, and when it rains, it pours and it brings rocks, it brings logs, it's a lot of heavy stuff, and it'll be all over the place if we anchor it, right? It'll be all over the place. We would have to design the components to be waterproof, water sealed, and it just builds up.
I hope it's water sealed.
No, it is, but when it's submerged, it has to be at another level.